This video is sponsored by Magellan TV. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. In our last video about the sun's gravitational lens, we talked about a plan to send solar sails 650 astronomical units from the sun. That's the distance where the sun effectively becomes a telescope with a magnifying power of about 100 billion. It's an ambitious project, but one that's becoming feasible thanks to advances in small CubeSats and lightweight solar sails. In fact, scientists are developing an advanced sail called the SunVane that will accelerate to 35 kilometers per second, or 7 astronomical units per year. Compare that to the New Horizons spacecraft. When it launched in 2006, it had an initial speed of more than 16 kilometers per second. That made it the fastest spacecraft ever launched. It got a gravity assist from Jupiter a little over a year later and reached Pluto in 2015, just 9 years after launch. That's an amazing achievement, but it's pretty much the fastest we can go with chemical rockets. But a sailcraft with an escape speed of 7 AU per year could reach Pluto in just 5.5 years. In other words, sailcraft have the potential to be the fastest and most economical method of exploring the outer solar system. We're going to talk about how solar sails work and the kinds of exploration missions we may very well see in the coming decades. But first, I'd like to thank Magellan TV, who are very kindly sponsoring today's video. Magellan is a new documentary streaming service featuring content that dives deep into topics such as history, art, nature, and of course my favorites, space and science. In fact, I was inspired to make this video after watching Faster Than Light, The Dream of Interstellar Flight. It's a great documentary about future propulsion technologies. New programs are added weekly and can be watched on Roku, Amazon Fire TV, Apple TV, Google Play, and iOS. You can even cast directly from your phone to your TV. Documentaries are streamed without interruptions, ads, or limitations to access. And you can enjoy a wide selection of programs, including Faster Than Light, in beautiful 4K at no additional cost. If you enjoy the content here on Launchpad Astronomy, then I think you'll enjoy Magellan TV. That's why I'm delighted to tell you about a special offer just for my viewers. By signing up at the link below, you'll get an extra month of Magellan TV absolutely free. Please make sure to use the link in the description. Sailing the solar system is hardly a new idea. In 1607, Johannes Kepler noticed that the tails of comets always pointed away from the sun. He speculated, quite correctly in fact, that the sun must be heating the comet and somehow blowing the liberated material into a tail. In his letter to Galileo in 1610, Kepler wrote that it might one day be possible to provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void. Although Kepler was also correct in his speculation about the solar wind, solar sails are actually propelled by the photons of sunlight. Even though photons don't have any mass, they still have momentum. That means when sunlight strikes a surface, some of its momentum is transferred to the object. The more reflective the surface, the more momentum is transferred, and the object feels a tiny force acting on it. How tiny? Well, if you could go outside on a bright sunny day, the total pressure of sunlight is roughly less than a small paperclip resting in your hand. Even the slightest breeze exerts far more pressure. But in space, it's a different story. Granted, it's the same tiny pressure that we feel here on Earth. In fact, it works out to about 9 newtons, or 2 pounds per square kilometer. That won't produce a very strong acceleration, even on a lightweight sail. But as long as the sail faces the sun, it keeps accelerating. If you wait long enough, the sail will build up a lot of speed with no fuel required. Sunlight will of course push a sail away from the sun, but a sail can also tack inwards toward the sun like a sailboat tacking into the wind. This is done by angling the sail so sunlight pushes against the direction of the spacecraft's orbit. This causes the spacecraft to lose angular momentum and fall inward toward the sun. Solar sails can control their direction in other ways. For example, Mariner 4 wasn't a dedicated sail, but it was equipped with 4 vanes mounted on the tips of its solar panels. The vanes used sunlight pressure to stabilize the spacecraft as it flew past Mars, and that was in 1965. In the early 1970s, the Mariner 10 mission to Venus and Mercury prematurely ran out of fuel for its thrusters. Engineers saved the mission by adjusting the angle of its solar panels to maintain attitude control. In the mid-1970s, the Jet Propulsion Laboratory designed a solar sail to rendezvous with Halley's Comet in 1986. Carl Sagan appeared on The Tonight Show with Johnny Carson to promote the idea. Although Sagan discussed a traditional kite sail design, NASA opted for a second design called the heliogyro. Instead of using struts to deploy a kite, the heliogyro would spin up and extend its 12 blades by centrifugal force. In order to achieve the required surface area, each blade would be 8 meters wide and more than 6 kilometers long. The spacecraft's attitude and direction would be controlled by changing the pitch angle of the blades, just like the collective pitch control on a helicopter. The heliogyro would tack into a slingshot trajectory around the Sun and then set off for Comet Halley, the same comet that captured Kepler's imagination nearly 400 years earlier. Although it could have been manufactured for less cost than a traditional spacecraft, the heliogyro was a large and complicated design. In fact, it was so large it could only be launched by the space shuttle. But the shuttle was behind schedule and over budget, so Congress canceled funding for new planetary missions in 1980, and the heliogyro was scrapped. It wouldn't be until 30 years later, when the Japanese space agency JAXA finally demonstrated the first solar sailcraft. The interplanetary kite, accelerated by radiation of the Sun, or Icaros, was launched in May 2010 as a secondary payload to the Venus Climate Orbiter Akatsuki. With a launch mass of 315 kilograms, Icaros deployed its sail by centrifugal force. It was made of polyamide and 20 meters in diagonal, but only 7.5 microns thick. Icaros used thrusters for attitude control during normal operations, but it also tested the use of liquid crystal displays for attitude control. By varying the reflectivity of individual LCDs, they could vary the amount of sunlight pressure acting on different parts of the sail. This allowed Icaros to control its attitude without the use of any propellant. NASA finally demonstrated solar sailing the following year when it launched the NanoSail D2 CubeSat. At just 4 kilograms, it was much smaller than Icaros. Because it was a secondary payload to low Earth orbit, it only flew for 240 days before burning up on re-entry. But it was the first demonstration of a CubeSat sailcraft. In 2019, the Planetary Society, which, by the way, was co-founded by Carl Sagan, launched LightSail 2 by hitching a ride on a Falcon Heavy. After deploying its Mylar sails, it faced the Sun through perigee and flipped edge-on to the Sun through apogee. That extra push from sunlight allowed the spacecraft to raise its orbit. Even though it orbits higher than the International Space Station, LightSail 2 still feels the drag of Earth's atmosphere. As a result, its orbit has been gradually decaying. The Planetary Society are still operating LightSail 2 and are learning a lot about how to optimize the sail's performance. This in turn will help the development of the next generation of sailcraft. To that end, NASA is developing the Near-Earth Asteroid Scout, or NEA-Scout. NEA-Scout's mission is to demonstrate the ability for a small 14-kilogram CubeSat sail to make a slow flyby of a near-Earth asteroid. Like all sail missions to date, NEA-Scout will be another technology demonstrator launched as a rideshare. In this case, on the first Artemis 1 mission to the Moon. Once it reaches cislunar space, NEA-Scout will separate from Artemis 1, deploy its 86 square meter sail, and set out for the asteroid. The target asteroid hasn't been announced yet because it will depend on when Artemis 1 actually launches. It's currently scheduled for November 2021. We'll see, but if it goes as planned, it could reach its target asteroid within 3 years after launch. Another mission NASA is considering is Solar Cruiser. This would be a much larger sail at nearly 1,700 square meters. Solar Cruiser would be launched as a, you guessed it, secondary payload to the Interstellar Mapping and Acceleration Probe, or IMAP mission. It's currently slated for launch in October 2024. If selected, the Solar Cruiser will study the Sun from a halo orbit around the Sun-Earth L1 Lagrangian point. This is the same orbit used by the Solar Heliophysics Observatory, or SOHO. However, solar sails aren't confined to the inner solar system where there's plenty of sunlight. On the contrary, they're our best chance for reaching the farthest regions of the solar system fast. Remember, it took New Horizons nearly a decade to reach Pluto, and that was because it was launched on the most powerful rocket available at the time. But it will need another century to reach the Sun's gravitational lens, or the hypothesized orbit of Planet 9. On the other hand, a sailcraft cruising at 300 kilometers per second could reach Pluto within a year, the heliosphere in 2 years, and interstellar space in 5 years. So how is it that a sail, which gains such low thrust from sunlight pressure, can outrace a traditional spacecraft launched by a rocket? Well, one of the solar gravitational lens's Phase 3 objectives is to demonstrate this very capability in a technology demonstration mission. Traditional kite sails are difficult to package, deploy, and control at large scales. And that's why the TDM spacecraft is using a new approach called the SunVane. The SunVane design breaks up the large sail area into smaller vanes that are distributed along a lightweight truss. This simplifies their construction and deployment. Not only that, but the vanes can be individually articulated, making the sail highly maneuverable. This allows the sail to rapidly tack inwards toward the Sun while minimizing its cross-section as it spirals in. At perihelion, the vanes are turned face onto the Sun for maximum acceleration. Afterward, the vanes make fine adjustments to its trajectory. Anyway, by the time it reaches Jupiter's orbit, the sunlight pressure acting on the spacecraft is too weak to accelerate the sail any further, and the Sun's gravity is too weak to slow it down. The spacecraft's momentum is more or less constant. The spacecraft can jettison the vanes to lower its mass and gain an additional acceleration. Now keep in mind, all of this requires zero fuel, and we haven't even considered possible flybys of planets yet. The technology demonstration mission is still in the early planning stages, but its goal is to come to within 10 solar radii and achieve an exit velocity of around 7 AU per year. That would make TDM 2 to 3 times faster than Voyager 1. At that speed, it will reach Jupiter in less than a year, Saturn in 2 years, and Voyager 1's distance in 20 years. As impressive as those speeds are, they're still not fast enough to reach the solar gravitational lens within, say, 20 years. Going faster with the solar sail means getting even closer to the Sun. Materials such as silicon nitride and silica are lightweight, reflective, and have high melting temperatures. A sail made of such material could come as close as 2 to 5 solar radii. That would allow them to reach cruising speeds of 300 kilometers per second or 25 AU per year. One of the SunVane's design goals is to be easy to manufacture at low cost. That could lead to mass production, economies of scale, and open up the outer solar system for exploration. Imagine sending a swarm of sailcraft to fly through the water plumes of Europa at Jupiter and Enceladus at Saturn. They could sample the water and test for the presence of microbes blasting out from the subsurface oceans. Water plumes on Europa were first discovered in 2016. The Europa Clipper will fly through these plumes when it launches in 2024. However, nothing is planned for Enceladus at Saturn, even though Cassini discovered its water geysers in 2005. And what about the nitrogen geysers of Neptune's moon Triton? They were discovered in 1989. There's even evidence of water geysers on Pluto. My point is that since the sailcraft are, by their very nature, fast and inexpensive, missions could be launched to investigate new phenomena shortly after they are discovered. We could always follow up with a large flagship mission later if needed. Then there's the rest of the Kuiper Belt. In 2019, New Horizons flew past Arrokoth, the first pristine Kuiper Belt object. But that was only possible because it happened to lie along New Horizons' flight path. More than 10,000 KBOs larger than 100 kilometers are thought to exist. Among them are the dwarf planets Haumea, Makemake, Eris, and Quaoar, all waiting to be explored. These destinations could be reached by small sailcraft in less time it took New Horizons to reach Pluto. Sailcraft would also be the fastest way to explore, or maybe even search for, the hypothetical Planet 9. Right now, our best hope of finding it is with the Vera Rubin Observatory's 10-year survey of the southern sky. But what if Planet 9 is so far away it's beyond the reach of even the Rubin survey? Or maybe it's closer, but it's unusually dark. Or what if Rubin just can't find it because of all those Starlink satellites ruining the night sky? Well, one way to find it would be to fly probes to where Planet 9 is thought to exist and measure any gravitational deflections along their flight paths. That would allow us to triangulate Planet 9's position and even constrain its mass. We could then bring our space telescopes to bear and get our first view of the planet. Then we could send a follow-up sailcraft to make a direct flyby. We could even use sailcraft to chase down and explore interstellar objects. In 2017, Oumuamua became the first known asteroid of interstellar origin. 2 years later, Comet Borisov became the first known interstellar comet. It's thought that as many as 10,000 interstellar objects, or ISOs, may be passing inside Neptune's orbit on any given day. A fast-moving sailcraft could intercept these ISOs and allow us to answer unsolved mysteries about their nature. For example, after swinging past the Sun, Oumuamua accelerated instead of slowing down. Was this due to outgassing, like a comet, solar radiation pressure, or some other mechanism? There would be no better way to find out than with a rendezvous and flying alongside to see how it changes. If Oumuamua had been detected early enough, a 100-gram sailcraft could accelerate to 60 kilometers per second and rendezvous with Oumuamua at its closest approach in about 8 days. Of course, that assumes Oumuamua had been spotted early enough. When it was actually discovered, it had already swung around the Sun and was on an exit trajectory. If a pursuit had been initiated at the time of Oumuamua's discovery, a sailcraft could have caught up with it a month later. Now imagine trying to do that with our conventional approach. We'd spend years building a dedicated spacecraft before launching it on the most powerful rocket we could build, and then wait years or decades even before intercept. Even then, we would only be able to do that if Oumuamua were discovered before it entered the solar system. Sailcraft could also help us map the shape and structure of the heliosphere. The solar wind races outward from the Sun at supersonic speeds until it collides with the collective interstellar wind of the galaxy. This sets up a bubble called the heliosphere. Since the Sun is moving through the interstellar medium, it's long been thought that the heliosphere should resemble a giant comet-shaped structure with a long tail in the opposite direction of the Sun's motion. But recent simulations predict that the Sun's extended magnetic field would instead channel the solar wind into a more or less bipolar outflow. This new model predicts that as the Sun moves through the ISM, interstellar hydrogen atoms slam into the concentrated solar wind and create a population of fast-moving ions. A fast sail mission could test for the presence of these ions at roughly 150 AU. Their presence or absence would prove or rule out this new model. Multiple fast sails could be launched into different directions and begin to map the true shape of the heliosphere. Eventually, they'd reach beyond 500 AU and sample the pristine, undisturbed interstellar medium. Directly sampling the ISM would allow us to better understand the abundance of the elements available for building stars and their planetary systems. Right now, we do this with surveys, but interference from dust along our line of sight reduces the certainty of our measurements. Direct sampling of the ISM would allow us to calibrate our surveys and account for interference. In other words, we'd know how much star stuff is out there. Of course, the ultimate sail mission would be to another planetary system. The Breakthrough Starshot initiative aims to reach the Alpha Centauri system with tiny nanosails weighing just 1 gram each. Instead of a slingshot around the sun, an array of powerful lasers would accelerate the nanosails to 20% the speed of light. In other words, 100 million miles per hour. At that speed, the sails could reach the Alpha Centauri system 4.3 light years away in just 20 years. Obviously, there's a lot of engineering challenges to overcome, such as how to make a fully functional spacecraft that weighs just 1 gram, how to build lasers that can beam them out of the solar system, and many others. But the sailcraft missions we've discussed so far, including those to the solar gravitational lens, would be the proving grounds for Starshot. Think of what we would learn about mass production, miniaturization, navigation, communication, interstellar spaceflight, and high-speed sailing. As the Starshot laser system is built out, they could be used to support these missions as well. This leads to yet another economy of scale that further lowers mission costs. Now keep in mind that one of the cost savers is that most of the technologies needed are agnostic of the mission, whether it's exploring the Kuiper Belt or imaging exoplanets at the sun's gravitational lens. The Solar Gravitational Lens mission will allow us to map the coastlines and oceans of an exo-Earth. In fact, I made a video about that very topic, so if you haven't seen it yet, I invite you to check that out when we're done here. My thanks to my Patreon supporters for helping to keep Launchpad Astronomy going, and I'd like to welcome my newest patrons, Tomana Chukwueke, Jeffrey Hollicher, Colin Patterson, Nelson Rees, Matt Walters, and NGC 6543. And a special thanks to Anna for her intergalactic sponsorship, and to Michael Dowling, Stephen J. Morgan, and Morrison Wild for their cosmological level sponsorship. If you'd like to help support Launchpad Astronomy for the price of a cup of coffee every month, well, please check out my Patreon page. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay home, stay healthy, and stay curious, my friends.